As promised, we're here back at another set of AMCs. This time we're covering last year's AMC12A. So here we go. Right over here we have a very simple expression. We just multiply this. You can get through this very quickly. 0, 1, 0, 0, 0, 1 minus 99999. So that's equal to 2. All right, this next question is a modeling problem. Basically, we say that the time is this, and it's determined by the length of the trail and the altitude gain. And the model estimates that it takes 69 minutes to hike on top of the trail if it is 1.5 miles and ascends 800 feet. So one thing we can do here is just write down an equation, right? Like, so you have A times, so length of the trail in miles, 1.5, plus B times 800 feet ascension. And then on the other hand, we have as well as if the trail is 1.2 miles and ascends 1,100 feet. So here we can just do a subtraction to get 0.3a plus minus 300b is 0. So then we would get a is equal to 1000b, and we can just plug this back in here, and we can solve for a. So for b actually. So 69 is equal to 1,500 plus 800b, and so b is equal to 69 over 2.3k, and that is equal to 3 over 100. This is b, and so a is equal to 1,000 times this, so it's 30. And so the question is, if it's this and this, then we can just plug in t equals 4.2 times, so that is how long it is, so it's times a plus 4,000 times 3 over 100. So this is just equal to 126 plus 120, and that is equal to 246. It's B. 2024 is written as a sum of not necessarily distinct two-digit numbers, so we get a bunch of two-digit numbers that add to 2021, and we want the least number of this. So it's like, since there are no constraints on repetition, you can just take everything as 99. You can take 20 of these to first reach 1980, and then take a 44 to reach 2024. It's very obvious that this is optimal. So 20 plus 1 is 21 numbers. What is the least value such that this is a multiple of n factorial is a multiple of 2024? First of all, like for that year, you should know what the prime factorization is. Last year, it was known that it's 2 to the third times 11 times 23. And so basically, you can just go like look at each of the factors, and you want to ensure that this thing divides n factorial. So this 23 dictates that n is at least 23. This 11 dictates that n is at least 11. And to get 3 copies of 2, all you need is a 2, 4, and then everything else later would always satisfy this. So this basically says n is at least 4. So you just take the largest. This is, you can check that this works. A dataset containing 20 numbers, some of which are 6, has a mean 45. When all the 6s are removed, the dataset has mean 66. So you can just assume that there are A6s. And so the rest are 20 minus A numbers that, let's say, sum to B. So like their whole sum is B. We don't really care about them. So when all the 6s are removed, the mean is 66. That's basically B over 20 over A is 66. We also know that the 20 numbers have a mean of 45. So like they add up to, or actually let me just to write this, keep the same form. We have B plus 6A is over A is equal to 45. Oh, sorry, this is 20. Yeah. So then we can just move things around by a little bit. So let's see. We have B is 1320 minus 66A. And also, B is equal to, B is equal to 900 minus 6A. And then so these two things are equal. And so you have 420 is equal to 60A, and A is equal to 7. So A is that's the number of 6s. All right, this next question has the product of three integers is 60. What's the least possible positive sum? So like the integers can be negative or positive, but the sum must be positive. So that's a constraint. So first of all, we notice that if all three of the integers are positive, it will lead to a very big number. And the best way to do that is to have them spaced most closely together, and their sum would be 12. So this already seems very wrong because compared to negative positive, you could get a lot more better solutions here. So like after experimentation, for example, you can try this maybe. This would give you a 6. Okay. You could also try 10, because you need to ensure that the bigger factor is big enough to make the whole thing positive. So for example, if you have 6 here, you're going to run into a lot of trouble with becoming negative with this for the sum. So when you take 10, you could get 10, -6, -1, and that's equal to 3. So this is the best way to do it. You can play around more to be sure. So for this next one, we have an isosceles triangle, and it looks something like this. So an isosceles triangle, A, B, C, and we have evenly spaced points here on the hypotenuse, and there are 24 of them. So from P1 all the way to P2024, and you want the vector sum of all the vectors stemming from B and into these P's. So first of all, we notice that P1 and P2024 are symmetric about the perpendicular bisector of AC. So if you put a perpendicular bisector of AC, you notice that like PI and P2024 minus I are symmetric about that axis. And we also see that this bisector passes through B. So this means that we can pair P1 and P2024 together, and their vector sum is actually going to cross out in this hypotenuse component. So if you consider, we can break down this BP1 into this component plus this component, and the BP2024 into this component and this component. And so these two would cross, and you would get double the distance from B to AC. So PI plus P2024 minus I, so BPI plus B P2024 minus I is equal to essentially, if you take the midpoint, let's call this BM, is equal to 2BM, is equal to 2BM. And so you have this essentially 1012 times of BM. And how big is BM? Well, this is very simple because this is root 2, this is root 2, this is 1, 1. So like all of these are 45, 45, 50, 90 triangles. So like you get a 2, or actually you just get like BM is equal to 1. So like this is just 2024. The magnitude of this, or this sum, is 2024. All right, for this next one, we have an equation of log and cosine sine, logarithm plus trig. So the first step, one of the instincts is that you put them into one log, and that is equal to 0. So then we notice that this inner part has to be equal to 1. And because sine cosine's range are -1 to 1, the only way to achieve this is if they're both 1 or if they're both -1. So we're going to do this by case. So like if they're both -1, sine 3 theta is equal to -1 implies that 3 theta is, well, if you draw the unit circle, it has to be here. So this is 3 pi over 2 plus 2 theta. So this would have to be 3 pi over 2, 7 pi over 2, and 11 pi over 2. And if you do more, you'll go out of range, out of this range. So theta here is equal to pi over 2 7 pi over 6, or 11 pi over 6. And then cosine 2 theta is equal to -1. Then you have to be here, which means that 2 theta has to goes for is pi plus 2k pi, right? Oh, sorry, here we also have a k. So then theta, we can directly solve, is equal to pi over 4. And the next one is if it's 3 pi, so it's 3 pi over 4, 5 pi over 4, or 7 pi over 4. And we notice that both of these, the relationship between these two equations is and. You need both of these to be true, and none of the solutions overlap, or none of the thetas can satisfy both at the same time. So no solution for -1. For 1, you can do the same stuff, right? So sine 3 theta equals 1. This means that we have to be right over here, and so pi, theta, what am I doing? Theta is equal to pi over 6, or 5 pi over 6, 9 pi over 6, or 13 pi over, which would go over bound. So like we get these three. And then cosine 2 theta is equal to 1 gives theta is equal to, well, the cosine is equal to 1 has to be this point. So this point right over here. Then it would have to be, it would have to be 0 or pi or 2 pi. And none of these match again. So like there's just no solution. M is the greatest integer such that both are perfect squares. What is the units digit of m? So if we let this be x squared and this be y squared, then we notice that y squared minus x squared, their difference is 2560. And that is equal to, well, here on the left-hand side, we actually have y plus x, y minus x. We notice that here we can decompose this into, let's see, so this is 2 to the, you can take out, this is 256 times 10, and that is equal to 2 to the 8 times 2 times 5. So this is 2 to the 9 times 5. Then we notice that in order to maximize m, we want x plus y to be as large as possible, right? Or another way you can think about this is that x plus y is literally equal to this thing, whatever monster this is, and we want this to be as large as possible. So like if this is big, then m is certainly big. So we want to maximize this factor, and then we consider how large this can be. So notice that the difference between these two factors must be even. So they have an even difference, which means that both of them must have a factor of 2, right? You can't have one of them not have a factor of 2. So you can give a factor of 2 to each, and then you can just pour all the rest of the factors into this previous factor. So then y plus x is equal to 1208, and y minus x is equal to 2. So then we can just figure out what x and y are. So for example, here we just find x because x is smaller. So x should be equal to 639. And notice we don't really want to actually calculate what m is. We notice that m is equal to x squared minus 1213, and we only care about the units digit. So the units digit of x squared is 1, and the units digit of this then is this minus 3, which gives a units digit of 8. So this is 8. You would be wasting a lot of time by calculating them. Now this next question is, alpha is the radian measure of the smallest angle here. So actually it's very obvious what the smallest angle is. It's just this angle that's opposite to 3. So one nice thing you could do is you could take tangent of alpha, and that's 3 over 4. And tangent of beta then is, well, the smallest there is the one opposite to 7. And the reason why we take tangent is because when you're adding tangents together, for example, if you want the tangent of alpha plus beta, alpha minus beta, you can calculate that only with tangent. On the other hand, if you have sine, cosine, the addition formulas require each other. Like they would require the other sine or cosine. So here we have these two things, and I think it's very natural here to try adding them. Like checking what alpha plus beta is, because Yeah, at first sight, if you look at the answers, two of them suggest that they are double or triple, but there are also some that suggest otherwise. So we're actually not very sure here, and I think it's pretty natural to try to add them up. So that is just going to be their sum over 1 minus their product. And so here we get, well, you can multiply everything by 96. So that would be 72 plus 28 over 96 minus 21. And that is equal to 110 minus 75. And that is, oh, sorry, this is 100, my bad. 4 over 3. So this here, tangent alpha plus beta is 4 over 3. And we notice that then this angle has the reciprocal tangent value of this angle, which suggests that since tangent theta plus tangent 90 minus theta is equal to, times is equal to 1, then we know that the alpha and alpha plus beta are add up to 90. So in other words, then these two add up to 90 degrees. So then beta is 90 degrees minus 2 alpha. They're exactly k positive integers such that the base is divisible by 16. Basically, the statement is trying to say that 16 divides 2b cubed plus 2b plus 4. So you can simplify this a little bit into 8 divides b cubed plus b plus 2. And then basically what this is trying to say is that b cubed plus b is congruent to 6 mod 8. And then you can just try each b, right? So b is equal to 0, gives 0, 1 gives 2, so this gives 2, 2 gives 2, 3 gives 27, that gives 3, plus 3 is 6, so this works. 4 gives, this thing would vanish because it has too many factors of 2. This would give 4, so this doesn't work. 5 gives, 5 is just negative 3, and this isn't sort of an odd function. So this would just give negative 6, or 2. That wouldn't work. 6 is negative 2, so this would give 6, which is 8 minus 2. 7 would give 6, and so both of these cases here would work. So we would want all the numbers within this range that satisfy these. So what we could do is, because this is a multiple of 8, so this is a multiple of 8, so this is where it's congruent to 0. And so we sort of want to start the cycle at somewhere where it's 1. So it's like we want b's to start from 9 and then end with, so it would go from 1, 2, 3, 4, 5, 6, 7, 0. That's one cycle, right? And then it would end with a 1, 2, 3, 4, 5, 6, 7, 0, where this 0 is 2, 2, 4. So like we have this many cycles, and for 5, 6, 7, 8, we see that 6, 7 works. So this is 2, and note that there are how many cycles here? There are 252 cycles, and each of them have 3 solutions. So this is times 3, and this is 756 plus 2. So this is k is equal to this, and the sum of their digits is 20. For this one, we see that AB is equal to 270 squared, to 720 squared. This is the common property in geometric sequences, and so you can try to prove that if you want. And then we can factorize the right-hand side. And basically what you're trying to do is you're trying to distribute these factors to AB so that they're as close to each other as possible. And you can the key to this problem is just experimentation and then guessing. So we can try putting the 5s together, and we would see that 24, very naturally, you would think about this, is actually very close to it. So this is already an okay sign. This would leave us with 2 to the 5, 3 to the 3rd. And then we see that this is naturally 32, this is 27, and they're already very close to each other. And you would realize that there's no better way to do this. So then you can just give the 27 to 25 and the 32 to the 24, and you realize that they're very, very close to each other. And so after calculating them, you would see that this is 400 plus this plus 35. This is 675, and this is 48214. So this is 7. This is 768. And then you could just be quite confident about this because they're actually fairly close already. If you're really not confident about this, what you could do is you can think about this in another. You can check this using some brute force. So it's like because you already know that this is one possibility. If you want something even closer, you notice that at least one of the factors has to have a factor of 5. So then you can just go on and test all the multiples of 5 between these. So here you would have this would be 134 plus 1. So 135. 135. And so like you can go on and list all the way until 765, which is 140, 152 plus 1, 153. And you would realize that none of these, so like these are like, so like 135 through 153 are all the results after you divide these by 5. And they're supposed to include only factors of 2 to the 8. They're supposed to divide this number right over here. And so you would realize that none of them can do that. And so therefore this is the best solution. So B is equal to 768, and then the sum of the digits is just 21. All right, here we have a graph, basically a function. And actually, to start this problem off, we can quickly graph what this looks like. Or at least we're going to graph these two components. So e to the x looks something like this. Then e to the x plus 1 is this shifted to the right, to the left by one unit, right? So like so like this is supposed to be 0, and this is -1. So at the same level, you have these 2 points. And then e to the negative x is if you reflect e to the x over the y-axis, and that would look something like this. So actually here we would see that it is very apparent that we have an axis of symmetry here between these two parts. And that would lead us to think that, like, okay, well, if I'm here, like somewhat to the left of this, the sum would actually be the same. Like if you have these 2 points and these 2 points, like the functions or like the components just simply swapped sides. And so you can actually prove this very rigorously. Basically, like if you have an x here, if you reflect this over -1/2, that would be x minus 1. That would be -1 minus x, right? So then their sum is equal to -1, which is double of -1/2. Then you can just plug this in and show that they're equal. So we see that the line of symmetry is just this. And if you were to flip this over this axis, this point, well, we're here, and then the point is here. So if you flip it over, it would become, well, this -1 would become 0, and the y would remain the same, right? So like this is x is equal to -1/2. You have something at x is equal to -1, and you can flip it over to x is equal to 0 at the same y. So this is just D. What is the number in the position of 1, 2? So here we have arithmetic progressions. Nice. Okay, so then one thing we could do is we could go like D, 2D, 3D, 4D. And then we see that, well, then we can just deduce what these are, right? There are actually many ways to do this. This here is basically this plus this, so this plus this is equal to this double, right? That's basically something straight you get from the property of arithmetic sequences. This then would be 24 minus 4D. Okay. The difference here is 16 minus 2D, and you would repeat this 3 more times to get here. So this is 48 minus 6D on top of 16. And then this here is, well, the difference to here is 48 minus D, but then this is, and then this difference is already sorry, this is the difference of 48 minus d. And to get here, you need 4/3 of that. So you need 4/3 of this plus d. Then you can just solve an equation, right? So it's like this minus this. So it's like this minus this should be double of this minus this, right? So this difference is, well, this minus this, that's just 2d minus 40 should be equal to double of this minus this, which is, well, this minus 60 minus, well, this would be, what is this? This is 64 plus 4 over 3d minus d, right? So they are equal, and then this would cross, and we would have 40 is equal to, if you move this over here, then it would be 2d plus 12d. This is 1/3 d, so this is negative 2 over 3d. So this is 14, and this would become 40 over 3d is equal to 40. So d is equal to 3. This is probably one of the less nice ways to do this. There's probably some other way. Like you can probably set some other d, maybe here would have been nicer. But anyways, we got d is equal to 3. So then you can just calculate what this is. This is equal to 12. This is equal to, well, this is 18, so this is 30, 46. And so this question mark here is the average of these two, which is 58 over 2, and that's 29. All right, every year there's always one or two of these Vietas. This is very obviously Vietas. It's an expression, a very symmetrical one about all the roots. So first thing you can just expand this expression. This will be 4 times, then this would be p squared q squared r squared p squared, plus 16 times the sum of their squares, and then plus 64. So this thing is, then you also know that PQR is 3, PQ plus QR plus RP is 1, and sorry, they're all negative, and P plus Q plus R is negative 2. So you get this information. So like this one you can already know is 9, right? And this is actually also fairly easy. This is equal to 2 times the sum. So let's call this the sum. Let's call this the, I don't know, let me give R, and this is P. Then this is just 2s squared minus 2r. Oh, sorry, s squared minus 2r. And this is equal to 4 plus 2, and that's equal to 6. So this we also know what it is. And the only problem we have is with this right over here. So how might we be able to compute something like this? And one instinct is to have this thing squared. So we would notice that this thing, after we square this, we're going to be left with a bunch of garbage that we want to discard. So like, let's call this box. All right, this box is equal to this, but then this would give a lot of garbage, such as if you multiply these two things together, you would get PQ squared R, and you get that twice. And so for each pair, you could make the same argument, and you would want to remove 2 times P squared QR plus PQ squared R plus PQR squared. And then you can notice that this is equal to PQR times P plus Q plus R, right? Like this. So this is equal to R squared. This is R squared. So this is R squared minus 2SP, right? This would be equal to, well, R is equal to -1. So this is 1 minus 2SP. SP is 6, so it's 12. So this is -11. So this is, then you can just put this back in, and you get 9 minus 44 plus 96 plus 64. This is equal to 160. This is equal to 35. So this is 125D. First thing we do when we see this is we can make something, we can make assumptions that make this whole problem easier, that make this whole problem easier. And it's that we can let all players be distinguishable and all the tokens be distinguishable. Then this would greatly simplify our process. And so the probability is just what we want over everything. All then, because of this simplification, can be written as, well, for player 1, we want to choose 4 of them. For player B, we want to choose 4 of them. And for player C, it's just the remaining ones. And then what we want is for one of them to have all of this, one of them to have all of this, one of them to have all of this. And so then basically we're going to choose a player to get all red. We're going to choose a player to get all the blues. And we're going to choose a player to get all the basically the only other one, to get all the whites. So this is going to be 3 factorial. And once this is done, we're going to give them all the reds and whites and blues, right? So that is fixed. And then for the blacks, well, whoever got red only has 1 spot left. So you're going to choose a black for that person. And then the other person who got white has 2 left. And so you choose 2 from those remaining blacks. So this is equal to 3 factorial times 6 times 10 over this mess, basically. 7 times 6 times 5 over 4 times 3 times 2 times 4 times 3 times 2, right? So then you can eliminate a bunch of things. So let's see. You can eliminate, you can eliminate this, you can eliminate this, and you can eliminate this. And then 10 can be eliminated. Here we have this you can move a 9 here, and this would give 35 times 11, which is 385, 4 over this. So the answer is 389. All right, we had a little misprint here, whichever organization gave this. But here we have basically 3 equations, and we want an expression. So notice that they're integers, and this always helps. And so like one of the things we could try is we can experiment with 2 of the equations. So for example, here we can take it seems quite nice to take a difference. So let's do this one minus this one. So it's c times b minus a plus a minus b is equal to 27. Then c plus 1, then you can just factor out a factor of a minus b, or actually b minus a. b minus a times c minus 1 is 27. Right. Then since they're all integers, both of these might be negative, right? You could have both of them being negative. Actually, let's take one more difference, because 27 has a lot of factors, but then we notice that the difference between these two actually does not have that many factors, and that would greatly help with reducing down the possibilities. So we would get b a minus c plus c minus a is 13. So b minus 1 times a minus c is equal to 13. And 13 is very nice because it's prime. So there are only this many possibilities. So you can check this, this, or this. We can just check each of these cases, right? So zooming in, b is, for this case, b is equal to negative 12. Then CA is 72 from this one. So like this one we can keep deriving about CA. And A minus C is equal to negative 1. So if two things multiply to 72 and their difference is 1, then you would find that A and C are, A is equal to, AB, the pair AB can be 9, 8, or negative 8, negative 9. Oh, sorry, they're negative 1, my bad. So this would actually be opposite. This is negative 1. Then A is 8, B is 9, or negative 8, negative 9, negative 8. So these are the two possible solutions for AB. And this first one, you would immediately realize that BC would be immensely negative, and this A would not remedy it to an 87. So here we would just take the negative 8, negative 9, negative 8, and seriously check this one. So here we have AB is 108 minus 8. Perfect. BC is 96 minus 9. Nice. And AC is 72 minus 12. So this, because it doesn't say that there are multiple or it asks us to minimize something, this is a solution, and therefore we can just find this right over here. So the answer is 96 plus 108 plus 72, and that this is 180, so this is 276D. Also, like, checking the other ones is actually also very quick. You would immediately, like, if you unfortunately wrote it the other way around, which is completely fine and normal, you would just have to do a little bit more work, but it's a reasonable and doable amount of work. Okay, here we're actually missing a diagram. Here we go. So this is the diagram that we're missing, and so basically we're gonna keep on moving the card, rotating the card, with this rule where the one diagonal takes the place of the other one, and it's always in one fixed direction. So the next one would look something like this, and the next one would look something like next one would look something like this. And so this is very similar to the other annoying question in the beginning about like 3, 4, 5, 7, 24, 25. Basically, you gotta like figure out trig relationships between angles. So what we could do is we can consider how much this rectangle has shifted in terms of an angle theta, right? So like this is the diagonal. So like if we consider C, this point C, in this triangle, right? So this is the original triangle, and it has this point C. After rotation, the C ends up here, so it's C prime here. And there's obviously the center that this rectangle always revolves around, and we can find this angle of CC prime and determine this information about this theta right over here. So this is 1, and this big BC is 2 plus root 3. And this means that then we can compute AC, right? So AC is equal to the square root of 1 squared plus 2 plus root 3 square. And this is equal to 8 plus 2 root 3, 4 root 3. And this is equal to, well, let's see, is there any nice way we could, not for now. So AC is equal to this. Then OC and OC prime, they're both equal, right? So then OC is equal to half of this. So it's equal to 2 plus root 3. And this is also equal to OC prime. Then we can apply a law of cosines very nicely, right? So C prime C squared, which is 1, is equal to OC prime squared plus OC squared minus 2 times OC prime times OC times cosine theta, right over here. Then OC prime and OC are both equal to this, and so this part is equal to 4 plus 2 root 3 minus 2 times 2 plus root 3 cosine theta. Then here we have that cosine theta is equal to 3 plus 2 root 3 over 4 plus 2 root 3, like this. So this is actually very, very ugly. And as I said previously, it's very nice to have tangents. So here we're motivated to first find sine and then tangent. So so 1 minus this thing squared would become 4 plus 2 root 3 squared minus 3 plus 2 root 3 squared over 4 plus 2 root 3 squared, the square root of this. So if this is just finding the sine of theta, and this would be 4 plus 2 root 3, and then the numerator would be, well, you get a 7 and you get a 4 root 3, 7 plus 4 root 3, like this. Is there any way we could expand this? Yes, it's just 2 plus root 3. This thing is 2 plus root 3. Right, and then sine theta over cosine theta is equal to this. Well, you see that the denominators are the same, and so like tangent theta is just equal to 2 plus root 3 over 3 plus 2 root 3, right? Right, and then we can rationalize this. You can multiply a denominator and numerator by 3 minus 2 root 3, and that's going to be equal to, numerator is going to be -3, right? No problem, it's negative. And then numerator is going to be 6 minus 6, which is very nice. Oh no, it's not. Yeah, it is. And then it's going to be plus 3 root 3 minus 4 root 3. So it's going to be, this is going to be negative root 3 over, positive root 3 over 3. So that is the tangent of theta. And this is actually just equal to 1 over root 3. And so this we could immediately recognize is the theta, the tangent value of theta equals 30 degrees, right? So like that is theta. And so every rotation takes you 30 degrees. And in order for B to, how many cards must be used until a vertex of a new card lands exactly back on B, is when, well, if you keep rotating like this, right, the vertex that will end up on B is exactly this point right over here, right? So it's like this opposite D point. And this D takes 180 degrees to get there, so it's A. In retrospect, though, like if this question was very convenient because the theta is exactly 30. If it were not, though, like, and we got a tangent after rationalization, what you would have to do is you're gonna keep trying, because you would basically want to try 6 theta, 8 theta, 10 theta, 12 theta, find smarter ways, cleverer ways to do that, and basically then you're guaranteed to eventually know about each of these options. All right, cyclic quadrilateral has these lengths, and with CDA given. What is the length of the shorter diagonal of ABC? So first of all, whenever you have cyclic quads, it's nice to first draw a circle. We have BC and CD are equal. BC and CD are equal. And DA is equal to 5. So DA, this is probably not long enough. DA is equal to 5, and CDA is 120. So this is 120, this is 3, this is 3, this is 5. What is the shorter, what is the length of the shorter diagonal? So we could very quickly know what CA is by law of cosines, right? So CA squared is just 9 plus 25 minus 2 times 3 times 5 cosine 120. Cosine 120 is negative 1/2. So this is equal to 9 plus 25 plus 15, and this is 49. So this is 7. So this is very convenient. And then we want to find also what BD is. All right, because BD is clearly shorter because none of the options are 7. So that says that BD already tells us is less than 7. And again, remember that this is a cyclic quadrilateral. That means it has a lot of nice properties. One of them is that opposite angles add to 180, and so like here we already have a 60 here. We know this length and this length, which means very quickly we can find what BA is by law of sines. Actually, you would first have to go and find, well, you can just run a law of cosines to find this, right? So so if we let BA is equal to x, right, then you would have 49 is equal to 9 plus x squared minus 6x cosine 60. Cosine 60 is 1/2. So this is x squared minus 3x plus minus 40 is equal to 0. And so x is equal to 8 or negative 5, but you wouldn't want that. So this is 8. And so a Ptolemy's would give you the answer very immediately. So BD is equal to 39 over 7. D. PQ are chosen uniformly and at random on AB and AC respectively of quadrilateral ABC. Which of the following intervals contains the probability that the area APQ is less than the area of ABC? Okay, interesting. ABC P, Q are chosen randomly. Okay. So P and Q are chosen on A and B, A, B, and AC respectively, and we want APQ to be at least is less than the area of ABC, right? Then we can we can just consider what this means. So it's like we to have APQ over ABC less than 1/2. What this is trying to say is we can express this in the sine area formula. This is sine theta times AP times AQ over AP times AQ over 1/2 sine theta AB times AC is less than 1/2. So in other words, after this cancels, basically we want AP times AQ over AB times AC to be less than 1/2. And don't forget, this is an equilateral triangle. So these are both equal. And so we can take for granted that, or like without loss of generality, we let everything be equal to 1, like all the sides. And AP and AQ are independent variables. AP equals X, AQ is equal to Y, that are chosen from 0 to 1, right? So this expression would suddenly become XY is less than 1/2. And so then we can just simply draw a probability graph. It would become geometric probability. So 0, 1, 1 is here. You have a graph like this. This is X, this is Y. And we want to know when XY is equal to 1/2. And when you have y is equal to 1, x is equal to 1/2. When you have x is equal to 1, then y is equal to 1/2. And anywhere in between, it will be, well, xy is equal to 1/2 is something that's like a parabola, right? So it would be something less than this, but greater than this. So this would actually immediately give us the answer, because it's a parabola, it takes this bendy shape that goes below this straight line connecting this point and this point, whatever, we can give them a name, DE. And it is clearly going to be greater than this. This is just bounded by 3/4 and 7/8. All right, here we have a recurrence relation. Usually on AMC's, recurrence relation is either there's a really nice pattern or you just brute force. But here, obviously, brute force until you find a pattern, right? So like here, we're actually not sure what to do at first. This is basically asking for the floor of this big expression. So this seems to be a little bit, we could first try to write this into this, right? So it's like, why would you want to have that? Maybe it's a trick. So like we'll first want to explore a little bit like this. Then we can try to cross multiply. NaN minus n is equal to n minus 1 an minus 1 plus n minus 1. Then we actually have something very nice, and it's that we can define bn as nan. So then this is actually bn minus 1. This is bn. So bn minus n, or actually we can already start moving terms, minus bn minus 1, which is this guy, is equal to 2n minus 1. Right, and then we know that, then we can try to find what bn is in general, because we can write this all the way minus bn minus 2 is equal to 2n minus 1 minus 1. And you could go all the way down to b1, or actually b2 minus b1 is equal to 2 times 2 minus 1, which is 3. Or actually, we don't want to write that out. So like this, we have all the way down here. So we would write this many equations, and we can try to compute what b1 is, right? b1 is defined as b1 is equal to 1 times nan times 2. So it's 2. This guy is 2. And after adding everything together, we notice very nicely that all of these would cancel out. This is in fact a very general trick. Like you can use this on a lot of things. Minus 2 is equal to this whole mess on the right, which is, how many equations do you have? You have n minus 1 equations. So this would account for the 1. So you would minus n minus 1. This is all the negative ones. And then plus 2 times this sequence right over here. So that is equal to n plus 1 times n over 2 minus 1. Right. And then you can just find out what Bn is, right? So Bn is equal to n squared plus n minus 2 minus n plus 1 plus 2. And so this is equal to n squared plus 2 plus 1. Then very conveniently, we can just obtain that an is equal to, well, an is bn over n. So this is n plus 1 over n. Then here, we want the sum of the sum of an squared, and that is n plus 1 over n squared. This is equal to n squared plus 2 plus 1 over n squared, like this. And we want this from 1 to 100. So for this one, we have a formula for that. That is equal to n times n being like the final number. Let me use capital N. N is equal to 100. N times n plus 1 times 2n plus 1 over 6. And plugging in 100, we will have 100, 101, 201 over 6. That would be, this would be 50, this is 3, this is 67, 5050 times 67 over 3, over nothing. So this is going to be equal to, well, 335. So this is 338350. This is sort of like the big base. And then you get 2 for 100 times, so you get plus 200. So you already get to 338550. And then you want to add this last weird mystery term. Now, as those answers suggest, this thing is somewhere between 0 and 4, or maybe up to 5. And we actually don't know exactly what this is. But there are many tricks to deal with something like this. One way is integration. And we use integration just to estimate this. So n would go from 1 to infinity, to 100. And we can draw a picture of this, right? So if this is 1 over x, this here, let's say, is x equals 1. This is x equals 2. This is very unrealistic, obviously. This is x equals 3, and then you would go all the way to x equals 100. 100. So let's say you have this. Here is 100. Actually, let me get rid of this right over here. This is very distracting. So what this summation is trying to find is basically the sum of the bars from x equals 1, which is this one, right? And this curve is 1 over x squared, right? So this is x equals 2 for n equals 3 all the way to n equals 100. So this is 2, 3, 4, 5, and all the way up to 100. Then we notice that this curve of 1 over x squared, we can integrate it starting from some point where we feel like the inaccuracy is going to be small enough. So we can arbitrarily choose based on feeling. We can go like, okay, let's say starting from n equals 5, I want to approximate that part with an integral with this line. So if I were to write that down, oops. The summation that I want is equal to the first term plus the second term plus the third term plus the fourth term plus from 5 to 100. And this part I want to approximate with an integral. So this is, then we would see that the integral that bounds this actually is, so well, the areas that this sum denotes is everything from 4, the bars from 4 to 10. And so the integral from 4 to 10 would bound everything within this. So this is less than or equal to this integral from 4 to 100, this one part. And so like here we have, if we add these things together, we would get, well, a 144, 24, sorry, not 24, 36, 24, still not 24, divided by 9 would give you 16 and 9. And then here for this integral, we have 1/3, 1 over, oh, sorry, this is the lower bound, sorry, yeah, no problem. 4 cubed minus 1 over 1/3 of 1 over 100 cubed. And so here we have something that is 1, and this is like what, 52 plus 9 is 61. 61 over 144. And this here we see is, this is obviously greater or equal to 0, but because it's literally a positive area. But then it's also very, very small. Like this is tiny compared to, let's say, 1/2. So you have something that goes from 0 to 1/2. And so the floor of this is obviously going to be equal to 1. And this is the only fractional component of this sum, returning to here. So if you look at this, integer, integer, the only thing that could have been a decimal is this part. And so this here would be definitely be, the floor of this part is definitely equal to 1. So it's just b, like this. So for this next question, we want to fence this board. A closed loop that does not intersect itself. The number of the numbers in the cells indicate the number of sides of the square of that square that are to be covered by toothpicks. For this next one, again, I have to emphasize the importance of playing around with the problem. So here, well, you can first play around, and then you immediately would notice that you can't choose this edge as to be a toothpick, because the moment you do that, you can never get to the other side. You get stuck on this side. Well, there's only one case in which you could, right? So like you could find this extreme case. This is something very easy to miss. And in fact, there are only 2 of these very special ones, and you see that two answers have a difference of 2. Actually, this would already give things away. This is the way they get you. But so aside from those 2 cases, so those 2 weird cases, the general case, or like the average case, would be where you have like one strand here, and they're arranged in some weird way. And in this case, you cannot choose this part. Then there are a couple of cases. So like to cover this one, then, since you can't have any of these, you either have this or you have this. So let's start with the case where you have this and you have this. Then we notice that for each of these ones, as we said, there's an upper strand and a lower strand. And basically, each of these would want to get touched by exactly one of these strands. So like, for example, for this one, I could choose the lower one, this one upper, this one lower, this one upper, this one lower, this one upper. Then what we would get is that we can always find one unique arrangement of the strands to satisfy this. So for example, here, you would get something like this. Actually, this is not a great example. Let me, let's say this one's also down. Then there's only one unique way you could satisfy this, and it looks something like this, let's say. And notice again, you can't touch this. So no matter where you end up, so it's like if you want to pass through this, so let's fix this and this. So like then if you want to pass through this, then you have to, no matter if you're here or here, you would have to go the outer ways to not touch this. Otherwise, you'd be touching this one again. So here we would see that given these 2 bounds, you would have to go through, well, there are 6 choices, each of 2 options. So this is the number of ways to choose if you put the 2 vertical bounds, or like the ones, the bound that the toothpick that touches the outer ones here and here. Okay, so let's move on to another case. So let's say we have we put this toothpick here and this toothpick here. We would notice then that you can't touch this, you can't touch this, and it's the same problem for a smaller range here. So like again, you can choose for each of these where upper or lower, and then you would get 2 to the 5th choices. And then notice we don't really need to care about this one anymore. There's no way we're gonna extend the fence this way anymore. You would always want to loop back like this. So like once you've touched this, you don't want to go on this side. So this to the 5th is a nice answer. And then here, if we put this bound here and here, this is actually symmetrical to the 2 to the 5th. And then finally, we have the case where both of them are inside here. And again, we don't have to care about this or this anymore. And you have 4 choices now, so 2 to the 4th. And then adding, remember, don't forget the 2. You would see a total of 128 plus 16 plus 2. And that is equal to C. So as I said, like the 2 is a very mean way to get you, right? All right, so here all the angles are actually within the first quadrant. You would see that pi over 16 is about here, 7 pi over 16 is about here. And so there's some nice symmetry that we would want to try to use. But then also we see that we can start by factoring this into something like this. Like, again, you have to play around and check for nice patterns like this. And this is one of the many nice patterns, and it's this. And of course, we know that the tangent of an angle and pi over 2 minus that angle are reciprocals. And then we would be motivated to try to derive some relationship or like something nice about an expression that looks in general like this, right? So like once we know something about this, then we can just plug things in and see if there's something nice. So here we have sine squared x over cosine squared x plus, notice pi over 2 minus x. If you take the sine of that, it would become cosine of x. Cosine x, sine squared x. So then we can rewrite into a common denominator, and because we have cosine sine, we want to put this into a double angle formula. So immediately we would have something like this: cosine to the fourth, sine to the fourth, and then the denominator would become sine 2x squared. And the numerator we can write as, well, we can add an 8 cosine squared x sine squared x and subtract 8 times the same thing. Then this part would become 4 times cosine squared x plus sine squared x squared, which this whole thing is 1, minus 8 times cosine squared x sine squared x, like this. So this is going to be equal to 4 minus, and then we can try to manipulate this into another sine squared x, sine squared 2x, like this. And we would get exactly negative 2 plus 4 over sine squared 2x, like this. Then plugging this back into here, so actually we this part then, if you evaluate, so like we know what this is, right? So then taking x equals pi over 16, we would have that this blue underline part is equal to negative 2 plus 4 sine squared pi over 8. And x equals 3 pi over 16 would give red underline part is equal to negative 2 plus 4 over sine squared 3 pi over 8. Then we also note that sine squared pi over 8 is part of the double angle formula for cosine, right? So cosine pi over 4 is equal to this. Then sine squared pi over 8 actually is just equal to 2 minus root 2 over 4. And sine squared 3 pi over 8 is equal to 2 plus root 2 over 4. So then you can just plug both of them in, and you would get 16 over 2 minus root 2 minus 2 times 16 over 2 plus root 2 minus 2. And this is equal to, you can put the 2 in, so that's 16 minus 2 plus 2 root 2 over 2 minus root 2 times 16 minus 2 plus minus 2 root 2 over 2 plus root 2. Multiplying them together, you get denominator 2, numerator 144 minus 8. So that's going to be 136 over 2, and that is 68. So the answer is B. For 24 and 25, we'll cover them in a separate video as last two. We're having our midterms recently, so I can't go into spending too much energy on this. So yeah, we'll save these for some time later. Thank you.